Here is a fully completed mathematical proof. A 26 billion parameter model accurately calculated the total mass of a spherical gas cloud using a triple integral over an exponentially decaying density function. But the text you are reading was not written sequentially from left to right. Before a single number or variable appeared, this entire page started as 256 positions of maximum entropy noise, a chaotic field of Arabic script, Cyrillic letters, Bengali characters, and stray HTML tags. On this generation grid, over 48 inference steps, blocks of coherent mathematics began crystallizing out of order. Equations locked early on, while surrounding spaces boiled with random noise. This proof was generated by DiffusionGemma operating via uniform state discrete diffusion. By stripping away standard autoregressive generation and replacing it with entropy-bounded annealing, we gain physical access to the model's conditional dependency structures. We see exactly which concepts it treats as independent and which it relies on for context. Under this architecture, the model is no longer predicting the next token. We are watching logical meaning physically crystallize out of a chaotic data field. To understand the mechanics of this noise, we have to look at the older paradigm for text diffusion models. This split screen illustrates the difference. On the left, masked diffusion starts with identical mask tokens, replacing them with words one by one. Once filled, that token is permanently locked into place. On the right side, DiffusionGemma uses uniform state diffusion. There are no mask placeholders. Instead, any position that the model is uncertain about is continuously redrawn from a uniform distribution of the model's entire vocabulary, all 262,000 possible tokens. A uniform draw across that many tokens creates 18 bits of entropy per position. It is a massive, high-speed melt of polyglot data. The wild cascades of katakana and stray code you see in the intermediate frames are not glitches. They are the literal, visible signature of maximum entropy categorical noise. Because unaccepted tokens constantly return to this chaotic melt, the model is never permanently stuck with a bad choice. This uniform noise provides the mathematical foundation for native self-correction. Replacing a single mask token with a 262,000 token melt shifts text generation away from a fill-in-the-blanks exercise. It becomes a continuous statistical phase transition. The most accurate way to conceptualize this process is as simulated annealing, in the strict statistical mechanics sense of the term. This phase transition is driven by a specific configuration called the entropy-bound scheduler. This graph tracks the inference run. The downward cooling schedule sharpens the probability distribution, and token entropy falls in tandem. A strict freezing criterion applies. When a string's entropy drops below the 0.05 bound, it freezes. Uncertain positions return to the melt. Meaning does not simply appear. It precipitates sequentially out of maximum entropy as the mathematical schedule cools below the defined error budget. If we examine the generation logs from our triple integral problem, we can observe exactly how the model builds its logical arguments. The data reveals a distinct freezing order. Core mathematical entities, specific numbers and variables like rho and pi, locked into place during the earliest inference steps. Meanwhile, the structural scaffolding, connecting words, syntax markers, and line breaks, remained as chaotic noise until the very end of the generation. We can map this behavior using a commit heat map, plotting token positions across generation steps. This freezing order is a direct readout of learned dependencies. Trajectory analysis confirms. Content and entities anchor first, while structural and function words settle last. This occurs because a token's identity is often contingent on the surrounding data. If a token flickers or stays unstable, it is waiting for information from its neighbors to settle. Mathematically, this temporal instability acts as a strict lower bound on how much mutual information that token shares with its unresolved context. The commit heat map is a direct measurement of the LLM's internal conditional dependency structure. We are watching the model prioritize foundational concepts before filling in the syntax that connects them. This nonlinear freezing order exposes a major advantage of uniform state models, the ability to change their minds mid-generation. This chart tracks the percentage of frozen tokens at each step. The model steadily climbs to a 100% commitment rate, generating a complete answer. But in the very next step, the commitment rate collapses entirely, dropping down to just 1%. This is a remelt. The scheduler evaluates the tokens at every step. If a newly locked token in the context pushes a previously frozen token's entropy back above the error bound, the frozen token loses its certainty. Those invalidated tokens do not stay on the board. They are instantly thrown back into the 18-bit melt to be redrawn and reevaluated based on the new context. This provides an observable self-correction mechanism. Because masked diffusion locks tokens permanently, this level of dynamic revision is structurally impossible in legacy models. We can push this diagnostic capability further by examining the comfy UI DiffusionGemma control interface. The sampler exposes several specific parameter knobs: the entropy bound, the temperature schedules, and the noise seed. A core rule of simulated annealing is that the final crystal structure depends entirely on the cooling protocol. In image diffusion, changing the sampler merely alters the aesthetic rendering. A Kara schedule and a Hoon solver will produce different visual textures of the same underlying subject. In text diffusion, the output is semantic. Changing the sampler crosses from how the text looks into what the text propositionally means. Adjusting the entropy bound directly alters the commitment dynamics. By changing the threshold for certainty, you force the model down completely different logical paths. This phase diagram maps how those paths diverge. The deviations can be categorized into two outcomes. Gentle settings produce stable regions of meaning-preserving paraphrases. Aggressive settings push the model over the boundary edge, resulting in completely different logical claims, known as truth flips. A text sampler's signature is not an aesthetic style. It is a specific disposition, carrying its own distinct set of logical failure modes. Treating text generation as an annealing process gives us a diagnostic instrument. We can observe the physical formation of logic the same way we watch crystalline structures form in a turbulent liquid. By manipulating the temperature and entropy boundaries, we finally have a shared vocabulary to probe exactly how a diffusion LLM builds, weighs, and structures its arguments. This level of visibility means we no longer have to guess at the internal state of a model. We can watch a claim form, identify exactly where the logic fails to hold, and observe it remelt when a better premise is found.